Today we're going to finish out our discussion about describing, exploring, and comparing data by talking about measures of relative standing and box plots. So the big idea here is we want to be able to look at measures of relative standing. These are numbers that show the location of data values relative to other data values from the same data set. So the most important concept that we'll talk about is the z-score, but we'll also talk about percentiles, quartiles, and we'll look at a way that we can graphically see those with a box plot. So a z-score is a standardized score or a standardized value. This is the number of standard deviations that a given value is above or below the mean. So we find it by taking our data value, subtracting the mean, and dividing by the standard deviation. We can do this with the sample mean and standard deviation, or with the population mean and standard deviation, and it works the same way. Whenever we're calculating z-scores, we always round them to 2 decimal places. So an example of a z-score might be 2.31. This would say that the data value is 2.31 standard deviations above the mean. So a z-score is the number of standard deviations that a given value is above or below the mean. For it being above, it'll be positive. For it being below, it'll be negative. Z-scores are expressed as numbers that have no units. A data value is considered significantly low if the z-value is less than -2, or it's significantly high if the z-score is greater than +2. If an individual data value is less than the mean, again, negative, and if it's greater than the mean, positive. So let's take a look at an example. So we're going to compare a baby's weight and adult body temperature. So we want to know which of the 2 data values is more extreme relative to the data set from which it came. So we have 4,000 gram weight of a newborn baby among 400 weights with sample mean of 3,152 grams and sample standard deviation of 693 4/10 grams. And our other piece that we're wondering about is a 99-degree Fahrenheit temperature of an adult. And this was taken among 106 adults with sample mean of 98.2 degrees Fahrenheit and sample standard deviation of 0.62 degrees Fahrenheit. So for both of these, we can calculate the z-scores. So our data point for the birth weight is 4,000 grams. Our mean was given to us as 3152. So we'll subtract that from our data point, and then we'll divide by the standard deviation that we were given of 693.4 grams. When we do so, we get a z-score of 1.22. So then let's look at the 99-degree body temperature example. So we take our sample point of 99 degrees Fahrenheit, and then we're going to subtract from that. There's a typo here. I really hope the average isn't that. Boiling blood is not good. So we're going to subtract the 98.2 with no 3 out in front of it, degrees Fahrenheit average, and we'll divide by 0.62, which will tell us that the z-score is 1.29. So now we need to interpret that. A z-score of 1.22 for the 4,000 gram birth weight tells us that 4,000 grams is 1.22 standard deviations above the mean, whereas the z-score of 1.29 for the 99-degree body temperature tells us that 99 degrees Fahrenheit is 1.29 standard deviations above the mean. This means that the 99-degree body temperature is slightly more extreme than the 4,000 gram birth weight. Again, neither one of these is actually significantly extreme, though, because if our z-score is between -2 and 2, it's considered to not be significantly extreme or significantly different than the mean, or if it's less than or equal to -2 or greater than or equal to 2, that z-score, then we have significantly different than the mean values. So we might want to know, is a platelet count of 75 significantly low? Well, if we say the lowest platelet count in our data set was 75, and we want to know if it's significantly low, what we'll do is we'll take the mean of our data set, 239.4, and standard deviation of 64.2. We were just given these values. You shouldn't have calculated them from anywhere. And we're going to take our data point of 75, subtract the mean from it, and divide by our standard deviation. Doing so gives us a z-score of -2.56. Since -2.56 is less than -2, that means that this platelet count of 75 is significantly low. Another measure that we use sometimes is called percentiles. So percentiles are used to tell us where in the data a value is located. What it does is it takes all of the data and breaks it up into 100 groups, and each one of those groups has about 1% of the values in it, and the percentile tells us which one of those groups it falls in. So to find the percentile, what we do is we take the number of values less than the value, and then we divide by the total number of values, and we multiply times 100. So let's look at an example. Here's Verizon cell phone data speeds, and we want to find the percentile for the data speed of 11.8 megabytes per second. So we look through our data and we count how many occurrences there are that are less than 11.8. That happens to be the first 2 rows of this data, which accounts for 20 observations. So we have 20 data speeds less than 11.8 divided by the 50 total observations we have, and we multiply times 100, giving us 40. That means that 11.8 megabytes per second is in the 40th percentile. We can loosely interpret this that 11.8 is like the dividing line between the lowest 40% and the highest 60% of values. So roughly 40% of the values fall below 11.8 megabytes per second. Let's talk notation real quick. So n, as it always has been, is the total number of values in the data set. K is going to be the percentile that's being used. So if we want the 25th percentile, K is going to be 25. Capital L is called the position or the locator of a value. So L for locator. And it tells us what position it is in the list. So the 12th value in the sorted list will have L equal to 12. And we'll use P with a subscript K. This is the kth percentile. So if I want the 25th percentile, I'll use a capital P with a subscript of 25, and that tells me the 25th percentile. Like in our example, we have P sub 40 telling us 40th percentile is 11.8. So if we want to convert a percentile to a data value, so we want to know what data value happens to be that percentile, we can follow this really handy flowchart. So we enter it at start, and it tells us to sort the data, arranging it lowest to highest. So we want increasing order. That's the way we want to sort it. All right. Then we're going to compute the locator value. We find L, our locator value, by taking our K value, our percentile we're looking for, divided by 100 times n, where n's the number of values of data we have, And that's going to give us an L value. Now we have to answer a question. Is L a whole number? It may be a whole number and it might not be. If it is a whole number, then we get to use this green box over here that follows the yes arrow to the right that says the value of the kth percentile is midway between the Lth value and the next value in the sorted set of data. So we find P sub k by adding the Lth value and the next value and dividing by the total of 2. We're finding the mean between those two, or of those two numbers. If, however, L is not a whole number, so there's some kind of fraction decimal thing happening, then we follow the arrow straight down, that's labeled no, to the red boxes, that says that we need to change L by rounding it up to the next larger whole number. And then the value of P sub k that we're looking for is the Lth value, counting from the lowest one. So let's take a look at an example. So we're going to refer to this set of sorted data, same set of sorted data that we had before, and we want to find the 40th percentile. So we need to calculate the locator. So to calculate the locator, we'll take 40, our k value, divide it by 100, and multiply it by 50 since there are 50 data values. That'll tell us 20. Now, since 20 is a whole number, we're going to follow the option box with the yes arrow over, and this tells us that we need to take the mean of the 40th, or of the 20th value, and the 21st value, the one after it, when we're counting up. So, if we go back to our data and we find the 20th and the 21st value, we'll find 11.6 and 11.8. So the value midway between them, the mean of those two values, is 11.7. So the 40th percentile, or P sub 40, equals 11.7 megabytes per second. Some really important percentiles that we work with are called quartiles. Quartiles are measures of location that we have special notation for of Q sub 1, Q sub 2, and Q sub 3. Quartiles, you might have heard the word quarter before, split the data into 4 groups. That means that there's about 25% of the data in each of the groups. Q1, Q2, and Q3 are the dividing lines to split up those 4 groups. So Q1 is called the first quartile. It has the same value as the 25th percentile. Separates the bottom 25% from the top 75%. Q2 has the same value as P50, also happens to have the same value as the median, and it separates the bottom 50% from the top 50%. And finally, Q3, or the third quartile, has the same value as our 75th percentile, separating the bottom 75% from the top 25%. Now, with percentiles and quartiles both, there are multiple ways that you can calculate them, and each of them is a little bit different. There's no universal agreement, unfortunately, which means that the values that you end up with could be a little bit different depending on how you're calculating it, making it incredibly important that you always show your work and share how you found these things with people. So, statistics that we can find using quartiles and percentiles, the most common is the interquartile range, or the IQR. This is simply taking the two interquartiles, so the 25 to 50% and 50 to 75%, and finding out how far apart is that third quartile and first quartile. So it's simply Q3 minus Q1, what's the range of those inner two quartiles? Hence the interquartile range. A couple of other statistics, again, a lot less likely that you'll run into them, a lot less common, are the semi-interquartile range, where we take that difference and divide it by 2. The mid-quartile range, where instead of subtracting, we add Q3 and Q1 and divide by 2. which tells us the midpoint of those quartile positions. And finally, I have no clue why the word quartile is even a part of this. The 10 to 90 quartile range, where we want to know how far apart is the 90th percentile and the 10th percentile. So we take the 90th percentile minus the 10th percentile. And again, the quartile thing, I don't know. I've got nothing because it has nothing to do with the quartiles, right? So when you're asked about a 5-number summary, or when we talk about a 5-number summary of some data, what we're looking at is 5 numbers that summarize the data. Those numbers are the minimum, the first quartile, the second quartile or median, the third quartile, and the maximum. 5 numbers summarized. All right, so let's find the 5-number summary of our Verizon airport data. So we go through this. The minimum and maximum are very easy. They're the smallest and largest numbers. First 2 numbers of our 5-number summary found, down to 3 that we need. We need quartile 1, median, quartile 3. So to find quartile 1, we're looking for the 25th percentile. And if we do that, we'll find that 7.9 is the 25th percentile. We're looking for the third quartile, 75th percentile. If we do that, then we're going to find that 21.5 is that third quartile. And to find the median, we're looking for that 50th percentile. And we'll find that it's actually between 13.7 and 14.1. So we'll need to take the mean of those 2 numbers and find that our second quartile or median is in fact 13.9. So our 5-number summary is our minimum of 0.8, our first quartile of 7.9, our second quartile or median of 13.9, our third quartile of 21.5, and our maximum of 77.8. Those 5-number summaries are great, but sometimes looking at the numbers, it's hard to really get a feel for how far apart are these things. And that's where box plots come in. And they're also called box and whisker diagrams or box and whisker plots. But a box plot is a graph of data that consists of a line extending out to the minimum value, a line extending out to the maximum value, and a box that has lines at quartile 1, quartile 3, and one in the middle at the median. It gives the 5-number summary visually. So if we want to construct a box plot, we need to find the 5-number summary, and then we need to extend all of these lines out and draw a rectangle. So let's look at doing one. Here we've got our same data, so we'll have our same 5-number summary. So here we have it. We have our 5-number summary of 0.8, 7.9, 13.9, 21.5, and 77.8. So we'll take our minimum of 0.8 and our maximum of 77.8. We'll mark them, we'll draw a line between them, and then on that line, we'll mark our first quartile, our second quartile, and our third quartile by drawing vertical lines. And then we'll connect the dots across the bottom and top of our vertical lines, making a rectangle that's formed by the sides of quartile 1 and quartile 3 markings and those horizontal lines that we filled in. This box plot that's shown here doesn't have a number line under it. It's a really good practice to put a number line underneath of your box plot so that you are actually marking these things to scale. It's really important for our box plot to be useful at all. It has to be done to scale. So we don't want to see something where the distance between 21.5 and 77.8 is the same as the distance between, say, 0.8 and 7.9. So a number line to help you make sure everything's to scale. Incredibly good practice. And also important that you label all of the values that are given. So you need to say what the minimum value is, what the maximum value is, and not leave it to the person who's looking at your box plot to interpret where those values are, because depending on the scale, it's very hard to tell whether it's 13.9 or 13.8. So label them. It's easy. Box plots are incredibly helpful in helping us identify skewness. We can see if the data extends out more one way than another, or we can see if it looks really nice and symmetric. And sometimes we want to identify outliers. Outliers are extreme values. And the way that we decide if a value is extreme enough to be considered an outlier is we take our interquartile range and we multiply it by 1.5. Then we take quartile 3 and we add that 1.5 times our IQR to it. And if there are any data values greater than that, they're considered outliers. And we take our quartile 1 and we subtract 1.5 times our IQR. And if there are any data values outside of that, below that, we consider them to be outliers. Sometimes we want to denote outliers in our box plot. A modified box plot does just that. So if we have any outliers, we use either like a round point or an asterisk or something to mark that data point that it exists. But then we move our minimum and maximum values down to the first value or most extreme value that's within that range of quartile 1 minus 1.5 times the IQR and below the quartile 3 plus 1.5 times the IQR. So we'll end up with a box plot, and there might be some asterisks or points out on either end of it. Or there might not be any if there are no outliers. And that's what a modified box plot is.